over one new announcement. I kind of doubt that many of you are interested, though you may be, okay? But there's a good chance you may know someone who's interested. This is a program that is being offered through our workforce development in partnership with Alabama Power, various utility and contracting companies, okay? It's a line worker training program. And as it suggests, it's basically training people to become the line workers for Alabama Power, other utility companies, Bell South, whoever has lines running on poles, okay? Line worker training program. Here's some of the information about it. Now, here's the bad news. Applications are being accepted today and tomorrow. I just printed this off yesterday. It may have been out there longer, but I didn't see it until yesterday. So today and tomorrow, the last 2 days to get your applications in. So if you know of someone who's been wanting to maybe get in on something like this, or been wondering about what they could do, and they like climbing and don't mind heights, that kind of stuff, I think it pays pretty well, and it's a great opportunity. The training duration actually doesn't start until June 8th and runs through August the 14th. The classes meet Monday through Friday, 8 to 4. So full 8-hour days, probably an hour for lunch for those 9 weeks. Okay, so it's pretty extensive training. The program tuition is $4,150 plus fees. Now the fees include books. Okay, I don't know how much they'll be, but they will be something. And I don't know what PPE is. Since it got you might, right? Okay. Anyone else come in? Okay. So I don't know what PPE is, but it's probably some sort of points for educate. I don't know. Then get this one, CDL physical, because when you complete the program, you have a commercial driver's license. So you get a commercial driver's license as part of this training, but you have to pay for the CDL physical. That's part of the fees. There are also permits, licensing, and exam fees. So there are a number of fees in addition to the $4,150. But don't let that discourage people, because scholarships are available. Evidently, they're really hurting for line people, line workers. So take advantage of this opportunity. Courtney, right? Okay, thank you. All right. Take advantage. If you know someone who's interested in this, encourage them to take advantage of this. It's a great training program offered here at the college, concentrated program. Lots of good stuff comes out of it. And the program outcomes, your OSHA 10 certification. Now, OSHA is Occupational Safety and Health Administration, I think. And that's OSHA 10 certification. That's pretty high. Commercial driver's license, like I said, you get that as part of the program. You also get cardiopulmonary resuscitation training, CPR training, and you get the basic line worker skills. So if you want more information, but remember, the deadline is tomorrow. More information, you can contact Lawson State Office of Workforce Development, Dr. James Gray. He's the Workforce Development Manager. And according to his phone number here, it's a 929-3519. I'm pretty sure he's either right across the way here in the Ethel Hall building, or he's behind us here on the other side of the building in Millsap building. Probably one of those two. I have his email address too, jgray@lawsonstate.edu, or you can contact Mr. Tommy Hobbs, who is the Assistant Dean for Workforce Development, and I'm pretty sure his office is in Ethel Hall building. That's why I think probably Dr. Graves is too, but I don't know that for sure. It's To apply in the program, there is a link. And so if you know of someone who's interested, please get this link for them. It's the www.eventbrite, and then a whole bunch of dots and slashes and dashes and everything else with pre-apprentice power line worker application tickets. Okay, so there's a lot of that's how you apply. So please, if you know someone who may be interested in this, get this information to them today or tomorrow, because tomorrow is the deadline for application. You won't hear that announcement again, because next time you're in here, the deadline will be passed. Okay. First thing I want to know, any questions on anything we've covered so far? Everything hunky-dory. I do applaud. This class has been very good about getting quizzes in. Just got another one this morning. I'd say well over half the class has got them in. We're in 1.8. When we finish 1.9, will be test time. You've got to have your quiz in before you can take the test. Preferably a few days before you take the test, so you can see what you missed on the quiz, because some of the quiz material, not the same questions, but testing you on the same material, will be on that test. Okay, shown, right?
Yes.
Okay, there you are. All right, good deal. Anyone else come in, Sister Caldwell? Okay, so please get the quizzes in so I can get them graded and you can see anything you may have missed. Not that many people are missing anything, but a few are. So, and most of the grades are out there on Blackboard, except the ones that have come in most recently. Okay. Let me, if there are no questions or anything we've done so far, let's move on. We're in Chapter 1, Functions in the Graphs, 1.8, Combinations of Functions, and this time we're talking about composite functions. This is sort of the new deal here. And we're getting ready to start example 6, top of page 79. Find the domain of the composition function f composed with g for the functions f of x is equal to x squared minus 9, okay, and g of x is equal to the square root of 9 minus x squared. Okay. You know, it didn't actually ask for the composition, but it's not a bad idea to go on and do it. So we will go on and do it. What first is the composition f composed with g of this function of x? First, what's the definition of that? What do we mean by f composed with g? What's the shorthand? Basically tells you what to do. Oh, it's been a long time since Thursday. Long weekend. What's the definition of that? Let's say again. F of g of x. Is that what you said? Please say yes. All right, good. Good choice. Okay. F of g of x. That's what the composition means. Okay. What do you plug in first? The innermost function, g of x. So leave the f out there, and then what is your g of x? You may have said it. What is it? The square root of 9 minus x squared. All right. Okay. Now, just a reminder, the f function tells you what to do with what's inside the parentheses. This says f of whatever's inside the parentheses is take that which is inside the parentheses, square it, and subtract 9 from it. Okay? So what are you going to do with this? That's what's inside the parentheses now, so what do we do with it? F, what does F do with it? Squares it, and then subtracts 9 from it. So let's first square this thing. The square root of 9 minus x squared. Going to take that and square it, and then we're going to subtract 9 from it. Okay? Now, what is the square of the square root of 9 minus x squared? Help me. What happens when you square root? Say again? They both disappear. One undoes the other. The square root undoes the square, and the square undoes the square root. So what are you left with? What's inside? Which is 9 minus x squared, and then subtract 9 from that. And what does that give us? Negative x squared. Okay. You have done it correctly. But if you look at this and say, remember what we're looking for? What is the domain of this function? If you look at that, you would say what? All real numbers. But you'd be wrong. Okay. Changes here. That's not wrong. Okay. All right. Now, here's what you have to do. Remember where you started with was g of x. So x has to satisfy g of x. Well, here's g of x. What restrictions does g of x place on x? Whenever you see a square root, you know that has to indicate what? What has to be under the radical of a square root? Say again? Not even. Okay. Not all real numbers. Which real numbers? Positive real numbers, or even better, non-negative real numbers. Okay? So in other words, what's under the radical has to be not negative, which means 9 minus x squared has to be greater than or equal to 0. That's what it means to be non-negative. Okay. Greater than or equal to 0. Let's solve that equation. Can we? Actually, whenever you have a squared equation, what should you do? What's the F word? Oh, y'all forgotten the F word already. Huh? Factor, okay? And does that factor? Does it factor? 9 minus x squared. Okay, I hear mumbling, but I can't make it out. It's what? Difference of two perfect squares. Say again? 3 minus x times 3 plus x. Remember, we called those conjugates of each other. Right? Huh? Right. Yeah, right. Has anyone else come in that I didn't acknowledge your name or presence when you came in? Okay. So this product here has to be greater than or equal to 0, right? Okay. Now, when is a product of two entities? John, right? Huh? Yeah. What products are always greater than or equal to 0? What about the two factors? And Even Kwame showed up today. Just a second there. I have to go all the way across the page. Okay, what were you saying? You have a product and it has to be greater than or equal to 0. What does that tell you about those two entities? They must be the same sign. So they could both be positive or both be negative, because when you multiply two negatives together, you get a positive, right? So either 3 minus x is greater than or equal to 0, and 3 plus x is greater than or equal to 0, or 3 minus x is less than or equal to 0, and 3 plus x less than or equal to 0. One of those two cases has to be true. So let's solve all of them and see what we get. So what will you do to this first one? A little louder. I hear a mumble. What's that? 3 minus x greater than or equal to 0. How would you solve that? Inequality. I like that idea. Add x to both sides. And that gives us 3 is greater than or equal to 0. Okay. Now, it's greater than or equal to x. That made no sense, didn't it? Okay. Greater than or equal to x. I added x, not 0. Well, my pen won't come on. Okay. All right. In other words, x is less than or equal to 3, right? That's the other way you could write that. X is less than or equal to 3. So let's do a number line up here. You can do it anywhere you want it to. Let that be 0, 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6, 7. Okay. Here is 3. And x is less than or equal to 3, so x is anywhere down this way, right? Including 3 and anywhere to the left. Okay? But and at the same time, what would you do to that? The second inequality there. A little louder. Subtract 3 from both sides. And these go away, then you have x is greater than or equal to negative 3. I'm going to do a different color here so you can follow me. What color you want this to be? Blue? Is that what you said? Green? Okay, I can't hear. Okay, x is greater than or equal to negative 3. Well, there's 0, negative 1, negative 2, negative 3. There's negative 3. It could be equal to it or greater than. Okay, so it's anywhere up that way. Well, this indicates that x has to be between minus 3 and 3 for it to fit that first one. That's the domain of G. We don't know if it's the domain of the composite function, but it's definitely the domain of G. Okay? So, but we still have this other one to mess with. So let's do that one. Let me go back to black. If we're solving this inequality, that's almost the same one we had before. We added x to both sides, remember? And that gave us 3 is less than or equal to x. It's just the opposite sign, which means if we turn it, if we turn it around, it'll be x is greater than or equal to 3. Well, in that case, now I need a different color. What color is that one going to be? Red, okay. This would be here and greater, okay. And, not just there, but also, and what we would do here, same as we did before, subtract 3 from both sides, and this says that x is less than or equal to negative 3. let's do that one in red too, because it isn't going to mess with it. Less than or equal to -3 is down there. Now, can anything be that red and that red at the same time? Can any number be down there and over here at the same time? Ah, so those are out. So since I got it red, I'm going to wipe that one out. That doesn't produce anything in the domain. This, however, does. Our green domain here is what we've got. So let's write it down. I think I'll go back to black here. The domain of G is the set, well, let's just do an interval notation. -3 to 3. That's the shortest way to write it. Okay, I don't really care for interval notation, but since I was running out of room there, I will write it that way. Okay, that's the domain of G. Okay, now, that's only part of the picture, because for this, the input for X, that's the domain of G from -3 to 3, but then the output of G is the input for F, because the range of G. Well, what values does G take on? Hint, that's a positive square root. It'll be plus, actually just 0 to 3. Because the maximum this could be is when X is equal to 0, which is in this domain, and the square root of 9 is 3. And then anything either going this way toward -3 or that way toward +3, these go down to 0, so 0 to 3 is all you've got there. But all those fit really well here. Anything could go in here. All real numbers could go in there, but we're limited to 0 to 3. So that's fine. Our domain for G is in this. That makes the domain for the composite function, because that depends on G, the same thing. To look at this, you say all real numbers. But to look at this, you say, nope, it has to be between -3 and 3. Now, they don't show this on the slide set, so let's read what we got. The domain of F composed with G is restricted to X values in the domain of G, for which G is in the domain of F. Okay? So F has any real numbers, all real numbers, that would be its domain. Anything that G spits out is going to be fine with F, which includes all the real values of G. So the domain of F composed with G is the entire domain of G, which is, as we just discovered, was -3 to 3. Okay. And they do show the plot in the book. Here is the graph of -x squared, okay, but you're only limited from -3 to 3, including the endpoints. So those endpoints are included. They didn't do a good job of making a dark circle there, but there is a dark circle, okay? So there is your output, okay? And F then, when this is -3, that would be -3 squared would be, okay, remember the output of that is 0 to 3. When this is 0, you get -9. Okay. To get a 0 here, you have to have plus or -3. That'll give you a 0 here. That's the output of this, then goes here, and a 0 here would be -9, and that's when your X is -3, this is -9, plus 3 is -9, and then when your input is 0 there, that is square root of 9 is 3 when you put a 0 in, and when you put 3 here, you get a 0 here. Okay, so you got to remember you got two functions going on, so sure enough, that is your function. That's how it looks, and it only goes from -3 to 3. Okay. All right. Now, any questions on that? I sent somebody came in, didn't I? Okay, what's the name? Say again. Yes, Latricia. Okay. Anyone else? Well, I didn't acknowledge when you came in earlier. Okay. Okay. So we've done example 5 and 6. And let's move on to the next slide. In example 5 and 6, you form the composition of two given functions. In calculus, which this is leading to, pre-calculus algebra, it is also important to be able to identify two functions that make up a given composite function. So before you were given two functions, you made one composite function. You also need to know when you have a composite function, how do you split that up into two functions? Two or more functions, in fact. For instance, the function h of x is equal to 3x minus 5 cubed. That's the composite of two functions. Can you see two functions there? Name one that you see. You see a function here? Besides 3x minus 5 equals cubed? Look deeper. Look innermost. It's the innermost function you have. 3x minus 5. That's a linear function, isn't it? And then the outer function is the cubing function. Okay, so you see this is a composite of a linear function inside a cubing function. Now remember, when we do our composite, the outer function goes on the outside, the inner function on the inside. So that would be the composition of f of x being the cubing function and g of x being the linear function that's on the inside. That is, the h of x is the g of x cubed, which is f of g of x, which you could then do one more step if you wanted to. I don't particularly want to, but you could then say this is f composed with g of x, because that's how it's defined. So, you just, before we were composing functions, now we are calling this decomposing functions, breaking them up into their component parts. Does that make sense? Okay? And when you get to calculus, this is what you do with a process they call the chain rule. You decompose a function and take derivatives that way. Basically, to decompose a composite function, look for the inner function and the outer function. In this function, this was the inner function, so that's the g of x on the inside. The f of x was the cubing function because that was on the outside, and so it's f of g of x because f of the inner function. Okay. Does that make sense? Okay. Whoa! They skipped example 7. So let's see if we can do example 7 here. Write the function h of x, say like h of x, is equal to 1 over x minus 2 squared. Okay? As a composition of two functions. Actually, you could do this as a composition of 3 functions if you wanted to, but 2 is fine too. How would you do that? What would be your innermost function? Say again? X minus 2, okay? So we usually, the innermost function, most of the time, they have it is the g. So let's just call that the g of x. So g of x is equal to x minus 2. Then what would be your outer function? F of x. Any ideas? Oh, it's requiring a little thought. That's really painful. Huh? What's that? be the outer function? F. Okay. If you said x squared, is that what you said, or 1 over x squared? Okay. If you do x squared, we're going to have to take it one more. So let f of x be x squared. Then you need yet a third function. Now you need to come up with a letter for it. What letter you want that to be? Not G or F or H. Some other letter. No. Huh? B. So your B of x, you got one other thing you've got going on here, don't you? That's the reciprocal function. Okay? So that would be 1 over x. Okay? So, they said 2, you did 3. This is B of F of G of x. Okay? Start with the innermost function. That would be B of F of, the G of x is x minus 2. Okay? Then do the F function, which is B of, and the F function takes whatever is inside x minus 2 and squares it. So that would be x minus 2 squared. Okay? Then take the B function, which is the reciprocal function, and that takes whatever's on the inside and puts it in the denominator. 1 over x minus 2 squared. There you did it using 3 functions. If you wanted to just use 2, you could have made the f of x 1 over x squared. That would have been fine, then you wouldn't need the b. Or you could have made the g function x minus 2 squared, and then made f 1 over x. That works too. There's several ways to do it. Actually, in calculus, you'd want to take it all the way down to 3. So I was surprised they asked you only to do 2 when 3 actually works better. Okay? But this is how it works. So there are multiple ways to do some of these. Okay? So unfortunately, when you use something like WebAssign, they're only looking for one answer. Okay? And they would say the others are wrong. Here is, let's see. I guess that's good enough. Okay. You did it well. You first chose the innermost function, then you chose the next innermost function, then you chose the outermost function. Good deal. So that's what we call decomposing 2 functions. Okay? Now, remember, after every one of these examples, there is a checkpoint. So please do the checkpoint shortly after you leave class. Now, before we move on to the application, you want a dumb story? Oh, you do? Oh, wow, I'm surprised. But it sort of relates to what we're doing. It really doesn't, okay? It kind of does. Never mind. Has anyone ever heard of Beethoven? Okay, now that's not the big dog that had lots of puppies. That's not that one. Okay. Okay? Who was Beethoven? Say again? Who? Made music. I mean, did he ever make music? One of the most famous composers. One of the 3 Bs. Bach, Brahms, and Beethoven. Okay? He made some incredible music. Huge symphonies. Da-da-da-da, da-da-da-da. You know, nothing but beats Beethoven's Fifth Symphony. That's just one of the masterpieces of the world. And he made many other symphonies. Now, I don't know the full history of Beethoven, but I've heard little bits and pieces. I've seen his picture, and he looked like a pretty grumpy old guy, but maybe that was just how they did pictures back then. But my understanding was he was such an intense musician that he probably didn't get along with people that well. I don't know that that's true or not, but he made beautiful music. I mean, it was just incredible, the music he made. But even way back then, music industry was pretty fickle, kind of like it is today. Can anyone name who won the Grammy 5 years ago? Probably not. I mean, you might guess and get it right. I don't know who won it. So yeah, you can look up on your phone, couldn't you? Okay, all right. And you can find it out. And it could be it's somebody that no one even listens to today. you know, or it could be someone who's still very popular. Music industry is pretty fickle. And even back then, it was a little bit, because Beethoven specialized in these enormous symphonies. But after a while, people got, you know, these enormous symphonies. These took a long time to listen to. They were very intricate. And some people wanted something a little lighter, you know, and chamber music or something like that. So the music taste changed. And then Beethoven liked symphonies, and he was still writing his symphonies, but no one was buying them anymore. Back then, there was no social security system. There was no fallback, no safety net. So he was basically getting more and more destitute. And he was getting older. Okay, that happens, unfortunately, okay? And as he got older, now this is what I've heard, he began to go deaf. How is that for a musician, huh? To go deaf and not have any music. Hey, he was such a good musician. He knew music inside out. I've heard that he actually cut the legs off of his piano so it sat flat on the floor. He sat flat on the floor and composed the music through the vibrations. He knew what notes went together, and he could feel the music. I don't know if that's true or not, but he was so good, I can't say it's not true. So anyway, but after a while, still nobody buying his music. He was getting in worse shape physically and stuff, and ultimately, he died. Okay? But he was poverty-stricken, probably living in some rented shack somewhere, you know, apartment, something, probably found by the cleaning lady, or you know the story. And so didn't seem to have any close family. I don't think he ever married, you know. So they just hauled him off to what they used to call the potter's field. You've heard of that? That's where people without any other means, the city buried them. Okay. Well, as usually happens in industries like the music and other things, there was a resurgence. And people sort of got tired of that little chamber music or whatever, and said, you know, where are the real symphonies, you know, like we used to hear? And by the way, whatever happened to Beethoven? And they started looking around and found out he died. What? Well, no one knew that, you know. He was one of the greatest musicians of all time. Well, where's he buried? Well, they found out in a potter's field over here. Unmarked grave almost. You know, they knew where it was, sort of. Oh, this will never do. He was one of the fantastic musicians that the world has ever produced. So we need to put him in a public cemetery where people can come and pay homage to him, because his music, there's nothing like it, nowhere. Oh, that's Stringman. Never mind. Okay, but anyway, so they had to go through all the mechanisms, to go through the city government and everything else to get permission to exhume the casket, the body, and put it into a more public, open mausoleum so people could come and pay homage. And it took a while. Finally, they got permission to do so. They hired some guys to go out there and dig up the grave. And as they were trying to listen, from what I understand, he was a pretty big old dude too, you know, so kind of heavy. And so they were lifting this old casket, and one of them sort of dropped the corner of the lid flew up. And there he sat, with sheet music in front of him, erasing like crazy. What was he doing? Decomposing. Never mind. Okay.
Well, of course he was decomposing. He was in the ground.
What's that?
I said, of course he was decomposing.
Yes, of course.
I wouldn't dig nobody up.
That was supposed to be the joke.
Yeah.
Yeah.
I know he stopped.
All right. Anyway, enough for dumb stories. Okay. Let's move on to applications. Okay. It's best if we came to that right at the end of the period, but we were right in the middle of it. So let's move on. Applications. The number N of bacteria, now that we're talking about decomposition, okay, in a refrigerated food, this is not a dead body, okay, well, it sort of is. Refrigerated food is given by N, that's the number of bacteria, as a function of capital T, where T is the temperature of the food in degrees Celsius. Now, we're not used to thinking of degrees Celsius, but so this is the, now, I don't like the wording of this too much. What they mean here, you've had food in the fridge, okay, and you pull it out, okay? When you pull it out of the fridge, it starts warming up, right? Okay, well, 2 degrees Celsius is 2 degrees above freezing Celsius, which is right around 36 degrees Fahrenheit. And if you check your refrigerator, if you have sort of a newer refrigerator, it may actually have the temperatures on the door, somewhere there. That's usually about what your refrigerator has, right around 36 degrees. That's approximate. That's 2 degrees Celsius. Now, when you roll it out and let it sit there a while, does anyone know what room temperature is in Celsius? Right around 20 degrees. 20 degrees Celsius is 68 degrees Fahrenheit, pretty close to room temperature. So this hasn't quite gotten up to room temperature yet. That's 14 degrees. So as the food warms up, bacteria, which have been sort of dormant in the fridge, they start multiplying. So the number of bacteria starts increasing as the temperature increases, and it uses this formula here. Not the bacteria knows the formula, but this is what they found by doing regressions and stuff. 20 times T squared, that's the temperature squared, minus 80 times T plus 500, okay? Where T is the temperature of the food in degrees Celsius between 2 and 14 degrees. When the food is removed from the fridge, that's what I'm saying, they should have said this up here, the temperature of the food is then given by, here's how the temperature changes. When you first pull it out of the fridge at time T equals 0, and T is equal to 0, the temperature at time T equals 0 is 2 degrees. Hey, that's good. That's where we started our formula from. And when it gets up to 3 hours, by the way, here, T, the little t is time, capital T is temperature. Little t time is in hours. 3 hours later, you put a 3 in here. 3 times 4 is 12 plus 2 is 14. It's reached 14 degrees. So basically it's saying it takes about 3 hours for that food to warm up from the 2 degrees it was in the fridge to the 14 degrees it is after 3 hours. Okay? So this is how long it takes the food to warm. Temperature is a function of time. This is number of bacteria as a function of temperature. So find the composition N composed with T of little t and interpret the meaning. So we don't have a lot of room to write here, but let's do what we can. N composed with T. What would that mean by definition? What is N composed with T? What's the definition of that? Composition. Y'all done it before when it's F and G. What is it now? Not that bad. Help me, somebody. N of, help me, T of T, okay? Capital T of little t. Yeah, that's the composition of N with T. Think of this as your of. N of T of T, okay? Think of it that way. Easy to do, okay? What do you plug in first? The innermost function, which is this one right here, right? T of T, the capital T of little t. So this would be N of, that little function, the T of T is 4 little t plus 2. Okay, then what do we do with that? Everywhere you see a capital T up here, you plug in this expression here. So that would be, I'll get it started, 20 times 4t plus 2, that's a little t, plus 2, what do you do to that? Square it, okay? Next, minus 80 times 4t plus 2 plus 500. Okay, good deal. All right. Now, we got a little bit of work to do. Okay. I'll write down the 20 again. I'll do that for you. Let's square 4t plus 2. Anyone do that rapidly in your head, or do you need to take a little time? There's a couple ways you can do it. Say again. What would that be? Remember the shortcut, or you want to do it foiling? I don't care. You tell me. Foil it or shortcut it? Foil it, okay? Let's go up here and foil it. This is 4t plus 2 times 4t plus 2. That's what it means to square something. Multiply it by itself. Okay, so what do you get? 4t times 4t is 16t squared. Then we do the outer. Plus 8t. Then we do the inner. Plus another 8t, right? And then we do the last. Plus 4. And besides the smiley face, you get what? 16t squared plus 16t plus 4. Now, you want me to review with you what the shortcut was? Square the first, 16t squared, plus twice the product of the two. The product of those two is 8t. Double that, you get plus 16t. That's exactly what we did. 8t plus 8t is 16t, and then square the last plus 4. So, you can foil it anytime you want to, or if you remember the shortcut, that's what it is. Okay, minus, let's go on and multiply that out. 80 times 4t is what? A little louder. 80 times 4t. Help me somebody, huh? 320t, is that what you said? Say yes. All right, I thought so, okay. And next, minus 80 times 2 is? Minus 80 times 2 is? Negative 160, all right. Plus 500, okay. Now, we still got that first part to do. This is what our n of t is, so this thing is still here. 20 times 16 is what? Is that 320 again? 320t squared plus, and that same thing, 320t plus 80. 4 times 20 is 80, minus 320t. Let's add those two together, and what do you get? Plus 340, is that right? 500 minus 160? Yay or nay? Okay. And then, notice what happens. 320t minus 320t adds to 0, and you get this n of t being 320t squared, and then plus 80 plus 340, I think is plus 420, right? Now that's your n of t of little t. Okay, we found the composition. There it is. Now, interpret the meaning of this in the context of our problem here. What does N stand for? Number of bacteria, okay? When now your independent variable is not temperature, but time. And this is time since you pulled it out of the fridge. Okay? So this is number of bacteria in that turkey after you got it out of the fridge. Okay? And what was it at time t equals 0? When you pulled it out of the fridge, it had 420 bacteria in it. You want to see what it has after 3 hours? Ooh. 9 times 320 plus 420. I think that's a lot more. Okay? Bacteria multiplied by dividing. Okay. Now, so we've answered that. Interpret the meaning and context. Number of bacteria as a function of the time since you pulled out of the fridge. Up to 3 hours. This is only good for that. So, the B part says, find the time when the bacteria count reaches 2,000. What's your bacteria count? Yeah, right. So then what we do is do 2,000, put that in for n, is equal to 320 t squared plus 420. What we're going to do is try to find that time, the t. Now, I'm running out of room rapidly. What would you suggest the first thing we do? I'll take this and write it up here, if that's okay. 2,000 is equal to 320 t squared plus 420. Okay, make sure I got that right. That seems awfully. Yep, 320 t squared plus 420. Okay. Now, what would you do first? Second, subtract 420. Is that what you said? Subtract 420 from both sides. And that gives you 1580 is equal to 320 t squared. And then what would you do? Divide by 320? Well, I'm going to first divide by 10, so wipe out the zeros to make it 32 into 158. Because I divided out the zeros. Someone with a calculator, tell me what that is. Say again? I can't hear. 158 divided by 32. Or 1580 divided by 320. I don't care. Either one works. 9? 4.9? 4.9 is equal to t squared. And how do we get, what time? How do you undo a square? Square root. Take a square root of whatever you had on your screen there, take a square root of it. What do you get? T is approximately equal to, it's going to be 2 point something, isn't it? Second? 2.2 hours later. Well, what's 0.2 of an hour? An hour is 60 minutes. 0.2 of 60 is 12, so that would be 2 hours and 12 minutes later. Okay? That's what time your count will be up to 2,000 bacteria. Let's see what they got. They said 2.2 hours. Now, what we did, and I neglected to point out that we were doing it, when you take the square root, you really almost always should do plus or minus the square root. But the minus doesn't make any sense here. Time doesn't go backwards. So this is 2 hours and 12 minutes later after you took it out. So you're just going to take the positive. See how we got it? They left it as 2.2. I just give it as 2 hours and 12 minutes. Okay. Now, there's a checkpoint following that, so please do the checkpoint shortly after you leave class. They have a little blurb there in the picture. Refrigerated foods can have 2 types of bacteria. Pathogenic bacteria, which I wouldn't want to have, which can cause foodborne illness, and spoilage bacteria, which give food an unpleasant look, smell, taste, or texture. Neither one of them are very pleasant bacteria, but as long as you eat them soon enough, they're not going to bother you. The pathogens could make you sick, though. All right. That finishes 1.8. There is a vocabulary, 2 questions at the top of the page. Let's do those, page 81. 2 functions f and g can be combined by the arithmetic operations of blank, 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 and blank to create new functions. What are your arithmetic operations? Your good old arithmetic operations. What 4 things did you learn back in 1st or 2nd grade? Addition, subtraction, multiplication, and division. Very good. To create new functions. Number 2, the blank of a function f with the function g is f little circle g of x. If I said what it was, I'd give it away, which is the same as f of g of x. What is that blank? Oh, come on, we're just doing it. The opposite of what Beethoven was doing, or what he used to do. Composition of 2 functions. Okay. So homework exercises here include number 3, which is found at calcchat.com. Any of the odds 5 through 11, they're all at CalcChat, but 11's at CalcView. Any of the odds 13 to 23, they're all at CalcChat, but 13's at CalcView. Either 25 or 27, they're both at CalcChat, 25's at CalcView. Any of the odds 29 to 33, they're all at CalcChat, 33's at CalcView. Any of the odds 35 to 41, they're all at CalcChat, 35's at CalcView. 43's at CalcChat. 45 or 47 are both at CalcChat, 45's at CalcView. 49 through 55 are all at CalcChat, 49's at CalcView. And then some applied problems, 57, 59, 61. So any of the odds 57 through 63. They all should be at CalcChat. Then there's a true or false. Number 65 should be at CalcChat. 67 should be at CalcChat. 69 is a proof. If you're really into proofs, you can do that one. You can write a function, 71. Those should both be at CalcChat, and another proof at 73 if you're into that. Now, are any of you, by the way, math majors? Too bad, okay? But if you're a math major, the proofs might be pretty beneficial for you to start practicing those. They're at CalcChat, so you can get some help there. Let's move on to, let's see how they did their problem. Okay, I did it all here. They're going to do it here. So what the composition of n with t, with the temperature function, is n of t, where n is number of bacteria, capital T is temperature as a function of little t time. And that says take the temperature function, put it inside the capital T for the n, so 20 times 4t plus 2 squared minus 80 times 4t plus 2 plus 500, just like we did. And when you work that out, it's 20 times, just like we got 16t squared plus 16t plus 4 minus 320t minus 160 plus 500. And then when you combine like terms there, or distribute, they haven't combined like terms yet, 320t squared plus 320t plus 80 minus 320t minus 160 plus 500. That gives us 320t because it's 320t squared plus 420 when you combine those things together. Because the 320t's add to 0. So that's your number of bacteria as a function of time, not of temperature. Okay? Time since the food's been taken out of the fridge. Okay? Then the bacteria count will reach 2,000 when you put 2,000 in for n. So they wrote it the other way. 320t squared plus 420 is equal to 2,000. Solve the equation. They don't show you how, but you know how. When that time would be about 2.2 hours. Note that when you solve that equation, you reject the negative value, because usually when you take square root, it's a plus or minus. But it doesn't make any sense to say 2.2 hours before you took it out of the fridge. That doesn't make sense. It wouldn't have had bacteria then. Not that many. So throw that away. Oh, and the other reason is, let's go back here. The little t, remember, oops, there it was. Little t is between 0 and 3. So 2.2 is in there, negative 2.2 is out. So therefore, we threw that away for that reason. Not in the domain. All right. Finally finished 1.8. Any questions on 1.8? Okay. Then let's move on to 1.9. We've got about 9 minutes, don't we? Okay. This is the last section in the chapter. So we, when we finish this, we are going to be ready for the test. But this sort of is another new topic here. Chapter 1 is functions in the graphs. 1.9 is inverse functions. We haven't done these before, so this is sort of a new topic. So our objectives here are to find inverse functions informally, which is kind of a, I almost want to say waste of time, but maybe it'll give you some insights. And verify that two functions are inverse functions of each other. That is worthwhile, verify. Then we'll use graphs of functions to determine whether the functions have inverse functions or not. That's usually pretty worthwhile. If you have a graphing calculator, you can just throw it up there and tell right off the top whether it has an inverse or not. Here's how you tell. You use the horizontal line test. We had a vertical line test to tell whether it's a function or not. The horizontal line test will determine whether the functions are one-to-one. Now, we haven't even defined what that means, but we'll get there. And then we'll find out inverse functions algebraically. That's how you'll do it most of the time, not informally. Algebraically is a little bit more sure process. You don't have to guess as much. So let's figure out what in the world we mean by inverse functions. So let's start with way back when we introduced functions. We know that a set of ordered pairs can represent a function. Remember? Set of ordered pairs, 1, 3, 2, 7, 5, 15, whatever. That can represent a function. For instance, the function f of x is equal to x plus 4. Okay? Now, this is a specific function from a set where A, the input set, also called the what input set? What's that called? It's a special name. We just talked about it a little earlier. Domain, okay? The domain function is 1, 2, 3, and 4. Those are the only function values for x for which f is defined. So what would be the values? When x equals 1, what would be your function? When x equals 1. What you get? 5. When x equals 2? When x equals 3? And when x equals 4? 8. Yeah, there's your B. It maps from this set to that set. Okay? So this is the function f of x equal x plus 4, but it's only defined for this set of ordered pairs 1, 5, 2, 6, 3, 7, 4, 8. 1, 5, 2, 6, 3, 7, 4, 8. That's mapping from one to the other. In this case, the interchanging of the first and second coordinates of each of these ordered pairs, you can form the inverse function of f. And when we talk about the inverse function, we'll give it the symbol f to the minus 1. Now, before, a variable or a number to the minus 1 means 1 over. That's not what it means when it's a function to the minus 1. That means inverse. So don't get those confused. They'll tell you about that later. So what would be the inverse function of this one? What would be the set of ordered pairs? If you exchange the x's and the y's, it would be 5, 1, 6, 2, 7, 3, 8, 4. That would be the inverse function of this function. Now, what would you guess the definition of that function would be. Well, do you think you get 5, make it a 1, 6, make it a 2, 7, make it a 3, 8, make it a 4? What was the function that does that? Subtractive. X minus 4, right? 5 minus 4 is 1, 6 minus 4 is 2, 7 minus 4 is 3, 8 minus 4 is 8 minus 4 is 4. Okay? So that would be the inverse function of this one. F inverse would be x minus 4. Better get to it later, but I'll go on and do it now. In this case, whoops, let me get my pen back. Yuck, it didn't come. Okay. There would be the inverse function, F inverse. Okay? That is the function that goes from B to A now. Notice what was your domain of the first function mapped into the range of the first function. Now when you do the inverse function, the range of the first becomes the domain of the second, and the domain of the first becomes the range of the second. Okay? So the function, inverse function is a function that goes from set B, which was the range, into set A, which was the domain, and that can be written just like we did as x minus 4, there it is, which is 5, 1, 6, 2, 7, 3, 8, 4. Note that the domain of F, the first function, is equal to the range of F inverse. The domain of F is set A, the range of F inverse is set A, and vice versa. The range of function F is now the domain of F inverse. Also note that the function F and F inverse have the effect of undoing each other. Guess what? You have been doing inverse functions all your mathematical lives. Because what did this just do? What undoes addition? Subtraction. What undoes multiplication? What undoes division? What undoes subtraction? Addition. What undoes the square root? A square. What undoes a square? A square. Yeah, you've been doing them your whole life. We have been calling them inverse functions, but that's what they are. Okay? Are we running out of time? What have we got? 2 minutes. Okay. Note that okay, we already did that one. Okay. So I have the effect of undoing edges. So here's the mapping diagram. If you start with the domain of F, F operates on this and puts it in the range of F, F inverse. Okay? The F function does this. Adds 4 to every one of these. 1, 2, 3, and 4. Add them, you get 5, 6, 7, and 8. The inverse function takes these values and subtracts 4 from them and moves them back into here. Okay? So the domain of F becomes the range. It becomes the range when the function operates on it. But then when the inverse function operates on it, it takes it from the range and moves it back to the domain. Okay. So I guess we're out of time. We didn't have a chance to do an example there. So we'll start right up here in other words, right there. And we didn't get to do any examples, so there'll be no homework from this section, but you got plenty of it from 1.8. So do your 1.8. Also be working on your quizzes. Get those in as soon as you can. Okay? Both of them have staples now. I'll put staples in the other. Good deal. Thank you. Thank you. Excellent. Way to go, class. Keep them coming, keep them coming. Okay. What's that?
Did you give us another quiz or this is the first quiz?
I can't hear you.
I said, did you give us another quiz?
No, this is the first quiz. Yeah. Yeah, you've already done your, no, you haven't yet. Oh, you did today. Okay, good deal. Thank you. Excellent.